This video is presented to you by NeuRoSpace, a company which is building the next generation of Moon Rovers and wants to take the opportunity to look back into the history of previous Moon and Mars rovers. It is a story full of pioneering spirit, exploration and engineering miracles. Welcome to the video series, The History of Extraterrestrial Rovers. In the last episode we talked about the first two unmanned rovers, the Moon Rovers Lunokhod 1 in 1970 and Lunokhod 2 in 1973. Actually, there were three more Moon Rovers between July 1971 and December 1972, the lunar roving vehicles by NASA, but they were manned and driven by astronauts during the Apollo missions 15, 16 and 17. As they are very special, the only manned rovers so far, we will cover them in an own special episode. So how did the history of unmanned rovers continue? The logical thought would be that the space agencies continued exploring the Moon, as it is the closest celestial body and thus perfect for testing and improving the performances of extraterrestrial rovers in general. But this is far from the truth. In fact, no space agency was interested in the exploration of the Moon's surface with rovers until China landed its Yutu-1 rover on the Moon in 2013. The focus was on Mars, although it is a lot harder to get and land there.
You have to keep in mind that the Moon and the Mars are actually a little different from each other. But that has a significant impact on the rover design. For example, there is a different length of days and nights, which results in a different temperature range. And the rover weighs twice as much on the Mars as on the Moon. Or, for example, the Moon completely lacks an atmosphere.
Especially the Soviet Union had many failures in trying to land on Mars. Only one probe made a soft touchdown on the surface, the first ever on Mars, but it only survived for 110 seconds. It was Mars 3 in 1971, and it even had the Soviet Union's only Mars rover to date on board, Prop M, which obviously wasn't able to do its job because of the loss of the lander. It would have been the first ever Mars rover. There was another identical Prop M rover on board Mars 2, which crashed onto the surface 9 days earlier. The Prop M rover had an interesting locomotion principle that worked with ski-like runners, and it is the only one of its kind to date, so props to Prop M. 5 years later, NASA had a successful soft touchdown on Mars on their first try with Viking 1 in 1976, which was the beginning of a Mars landing success story, making NASA the only agency to land things on Mars for 44 years, until again the Chinese came in 2020 with Tianwen-1, which also carried the first Chinese Mars rover, Zhurong, to the surface, but more on that in a later episode. So NASA gained more and more confidence in landing on Mars because Viking 2 was another success, and so in 1997 the first ever operational Mars rover, Sojourner, made it to the surface with the lander Mars Pathfinder in the Ares Vallis in Cruce Planitia. The name Sojourner was chosen from a naming competition held by the Planetary Society and the JPL. The winning paper was written by 12-year-old Valerie Ambroise, who suggested dedicating the rover to Sojourner Truth, a Civil War-era African-American abolitionist and women's rights advocate. In contrast to the first Moon rover Lunokhod 1, which was a giant, Sojourner was tiny, in fact the tiniest rover to date. Its dimensions were 65 cm x 48 cm x 30 cm. It had a mass of only 11.5 kilograms and it was cost efficient in the realm of space technology, with the development costs being only $25 million.
It's really quite impressive what the Americans have already achieved over 25 years ago. After all, the rover has a very similar size to what we are aiming for at NeuRoSpace right now. That's why we like to take inspiration from Sojourner for our rover.
Although it was so small, it was a fully functional rover with cameras, sensors, experiments, solar cells, a deployment mechanism, communication technology, thermal control, autonomy, a robotic arm and a new chassis design called the Rocker Boogie, which allowed it to move over uneven terrain with 6 wheels, each having an own motor and gear, as well as stainless steel spikes for traction, and being 13 cm in diameter and 7.9 cm wide. The Rocker Boogie mechanism basically consists of 2 rockers and 2 joints. The first, called the rocker, has its joint attached to the main rover body, and the second, called the bogie, has its joint attached to the rocker itself. Both sides of the chassis are connected via a differential gear to prevent the rover body from just tilting around its main joint and to ensure that all wheels always touch the ground. Each of the 4 outermost wheels could be rotated around its vertical axis in order to turn the rover. This chassis proved to be so successful that it should become the main design for all future rovers, not only by NASA but also by China, not counting the special jumping-like locomotion of the asteroid rover Mascot, which explored asteroid Ryugu in 2018 and was designed by the German DLR. One middle wheel of Sojourner also had an experiment attached, the wheel abrasion experiment. As the name implies, it measured the abrasion of different materials caused by the Martian surface. Thin films between 20 and 100 nanometers of aluminum, nickel and platinum were deposited on black anodized aluminum. By only moving this one wheel, it scratched on the surface, and the abrasion was measured optically by analyzing the amount of sunlight reflected from the scratched surfaces with a photovoltaic sensor. Sojourner had fixed solar cells on its top, which generated 15 watts peak power and 9 additional non-rechargeable lithium thionyl chloride batteries with about 300 watt-hours of energy for backup and nighttime operations. The batteries alone would have had enough energy for the whole 7-day primary mission. Another experiment regarded the solar cells and how they were affected by Martian dust settling on them, called the Materials Adherence Experiment. The scientists used a small solar cell which was covered by a movable cover glass. Once every Martian day, the cover glass was removed and the output currents before and after were compared in order to derive the loss of power due to dust. It turned out to be about 0.28% per Martian day, regardless of whether the rover was moving or stationary. A second sensor even measured the mass of the accumulated dust by measuring how the frequency of a vibrating quartz crystal changed due to the tiny dust mass. The rover was able to survive the cold Martian nights through its ingenious thermal management. All the critical components like the electronics were inside the so-called warm electronics box or web. It was made of fiberglass face sheets, aluminum spars and, most important, aerogel for thermal insulation. In combination with 3 radioactive heating units, the electronics waste heat, thermal strapping for heat conduction to the desired areas, and an active system which generated additional heat with resistor arrays, the temperature inside the web never fell below -40 degrees Celsius or climbed above 40 degrees Celsius. Sojourner could use its alpha proton X-ray spectrometer, which was mounted on a small robotic arm, to find elements in the rocks and soil. A curium-244 source emitted alpha particles, and when they hit the target, 3 components of return radiation are generated: Rutherford backscattering, production of protons, and generation of X-rays, depending on the mass of the elements. The spectrometer could measure all 3 components and thus was able to find various elements. Additionally, a color camera made images of the target area and the rover tracks. There was a strong symbiosis between the lander Pathfinder and the rover. The lander was responsible for communications from the rover to the Earth and back, and its images were essential for rover driving. Due to the time delay of signals between Earth and Mars and the low data rate, the rover could not be driven simply with a joystick, so the engineers came up with some ingenious methods to control the rover. Stereo panorama images of the lander, combined with stereo images taken with the rover's 2 monochrome front cameras, were used to generate a 3D graphical interface with the software on Earth. The driver used stereo goggles and placed virtual waypoints on the terrain where he wanted the rover to go. The rover then used its gyroscope and counted wheel revolutions for estimating travel distance to navigate to the waypoint, with a maximum speed of 1 centimeter per second. Exceptional autonomy features supported the operation. Would Sojourner have lost telemetry due to driving out of communications range of about 500 meters from the lander, it would have been able to return to the location where it last had contact. Additionally, Sojourner had an obstacle and hazard avoidance system. By shooting 5 laser stripes onto the surface and analyzing how they are reflected, an obstacle or hazard could be detected using various criteria. Once an obstacle was detected, the rover turned until the obstacle was out of sight, and then moved a wheel radius forward before stopping and doing the scan again, always updating its current position relative to the waypoint. And all this was done by only a 2 MHz CPU and 64 KB of RAM, that is about the RAM of a simple calculator. 2 fun facts for the end of the video. First, a second identical rover was built called Marie Curie for verifying complex commands on Earth. NASA first planned to send it to Mars too in 2003, but later decided to transfer it to the Smithsonian National Air and Space Museum in Washington, D.C. Second, Sojourner and Pathfinder had a cameo appearance in a movie. It was The Martian from 2015, directed by Ridley Scott and starring Matt Damon.
Sojourner was a really small Mars rover, and if you look at the history of lunar rovers, you won't find a similar rover of this size. This is currently changing, and NeuRoSpace is part of this new era of moon exploration. Be curious about Sojourner's little siblings on the moon.